So good evening, everyone. Tell what is answer for this question. Yes, right. 1.9 ohms is correct. 1.9 ohms is the answer. A 240-volt DC series motor initially drawing from 40 amps at 1500 RPM. So this is the back EMF initially. Now given the value of resistance which must be added to obtain rated torque at 1000 RPM. We need to reduce the speed. So adding a resistance to obtain the rated torque. Torque is the condition. So now we need to add some resistance in series with armature to obtain rated torque at 1000 RPM. The speed we have to reduce to 1000. Voltage is same, 240 volts. Resistance, how much to be added? That is the question. EB2. Now what is back EMF EB2? Tell me. This is IA2. IA2 we need to calculate. How to find IA2? If it is T1, here T2. So torque should be same. To obtain a rated torque means same torque in both cases. T1 equals to T2. Torque in series motor proportional to IA square. IA1 square, IA2 square. A square on both sides. IA1 equals to IA2. Both are same. IA2 equals to IA1, that is 40 amps only. EB2 is now 240 minus IA2 is 40 into sum of the resistance 0.3 plus external resistance. Same procedure. N2 by N1 equals to EB2 by EB1 phi1 by phi2. What is the flux in both cases? Same, cancel. Because current same, no? Same current in the field winding, 40 amps, 40 amps. Flux proportional to IA. Same current, same flux, cancelled. Now, N2 is 1000, N1 is 1500, EB2 is 240 minus 40 into 0.3 plus RE, EB1 is 228. Calculate RE value from this 1 point. Nine, right? Okay. So previously in last class we completed resistance control. Now one more last method remaining is voltage control method. Let's see the third one, voltage control method. Voltage control method. Now tell me, this voltage control is best suitable for which motor? Which for which motor voltage control is best suitable? Shunt, series, separately. Shunt, series, separately. Okay. Okay, let us consider shunt motor, check it is suitable or not. Take a shunt motor. Take a shunt motor. Suppose in a shunt motor, voltage is reduced by half. Initially, shunt motor rotating at 1000. Now, the voltage of the shunt motor reduced by half. What is the new speed of motor? Tell me. 1000, 500, 2000, 4000. What is the answer? If the voltage reduced to half, the speed of shunt motor is dash. Which one is the answer? The voltage reduced to half. The answer for this question is 1000 only. 1000 only answer, because the speed of shunt motor almost constant. It won't change. The speed of shunt motor is almost constant. Why? Because in a shunt motor, see, in a shunt motor, field current proportional to voltage. That's why voltage V first. ISH equals to V by RSH. Speed N proportional to EB by 5. Approximately, neglecting that IARA drop, this is V minus IARA, neglecting that IARA. Now this is V by 5. So whenever voltage reduced by half, flux also reduced by half. then the ratio is again V by 5 only, no change in the ratio, almost same. That's why voltage control not at all suitable for shunt motor. It is the best suitable for separately excited motor only. Okay, separately excited motor only it is suitable. Because in separately excited, field current, if you change voltage, field current will not change. That remains same, constant, flux also constant. That's why it is not suitable for shunt. It is suitable for only separately excited motor because of this reason. Now tell me, series motor, every motor, if you take series motor also, when voltage changes, current changes, flux will also changes. So series motor also purely not suitable. You can use for series motor. When voltage change, series motor speed will change. But in case of shunt motor, it is almost constant. Okay. Now let us consider a separately excited motor first. Separately excited motor. Here armature voltage is separate, field voltage is separate. This is called voltage control or armature voltage control because voltage across armature we are changing. When this voltage is changes, tell me first, with voltage control, what are the speeds possible? Below rated, above rated, both. V minus IARA by 5. Flux is constant, we are not changing flux. Resistance, we are not changing. So, speed proportional to V. Whenever voltage decrease, speed decrease. Whenever voltage increase, speed increase. Now, which one is possible? Below rated, above rated, both. After 20 years means how can we say, Malish? Okay. Actually, theoretically, both are possible. Theoretically, you can increase. Theoretically, when voltage decrease, speed decrease. When voltage increase, speed increase. But practically, for every motor, so this point valid for every motor, not only DC motors, induction, synchronous, anywhere. What is the practically we can apply? Suppose initially rated voltage given, rated voltage. Now the motor is rotating at some rated speed. Now what is the possibility? What is the possibility? Practically, we can reduce the voltage. We should never increase the voltage above rated value. If voltage reduce, speed reduce. If voltage increase, speed increase. But practical possibility is reduction of voltage. We should never increase the voltages for any motor above rated voltage. That's why above rated speeds never possible with voltage control. Only below rated speeds are possible. Okay. Now, only below rated possible. Why it is not possible above rated? Because each and every motor, whatever we are designing for rated voltages. If you buy a ceiling fan or any hydraulic motors, anything, on the nameplate, if you see there is some rating, voltage rating, 250 volts or 240 volts, like this. Means this fan is designed for 240 volts. So how much voltage you can apply? Up to 240, no problem to motors. But if you apply more than that, some 300 volts or 350 volts, what happens to motor? Damage, definitely. Why? The insulation internally designed for 240 volts. Insulation, the insulation of the winding, if you observe, on the copper wires also we have some insulating coating will be there. On the copper wire itself, there is insulation coating. And that will damage. And we use some impregnated papers like that in slots also. That is also damaged. So due to that reason, every insulation for every motor we design for the fixed voltage. So in future, if you want to increase the voltage, you cannot operate that motor. But anyhow, always we operate at one constant voltage. Voltages we never change. Single phase means 220, 230. In that range almost we get. Every time, permanently we get same voltages. More than that we don't get, and less than that we never get. We will get low voltages, high voltages, rarely, dangerous case. But generally we operate at 220, 230. That's why the rating is designed for 240. But why they don't design the motors for higher voltages? They will design, they can design for higher voltage, but why they are not designing? Because nobody will buy that. Why? The cost of motors mainly proportional to insulation used in that. If insulation increase, why insulation increase? Insulation proportional to voltages. If you want to increase voltages, insulation should increase. Then what is the cost of that motors? Also increase. Then who will buy that? Okay. For economical purpose, we never add more insulation unnecessarily in the motors. We fix some voltage, some rating, and insulation also designed for that same voltage, 240, 250 around that. Not more than this. That's why we should not increase practically the voltages. Whenever voltages you increase, internal insulation may fail and winding to winding short circuit may take place. So to avoid that, the only possibility is to reduce the voltages, but not increase the voltages. That's why with voltage control, that may be DC motor, that may be induction motor, only below rated speeds are possible. Above rated, never possible. Okay. Okay. Now we confirm only below rated. Now our task is here to reduce the voltage. How to reduce this voltage? Tell me. How can we reduce this voltage? By using auto transformer. Right or wrong? By using auto transformer, we can reduce the voltage. Is it right or wrong? Yes, that is wrong. Why it is wrong? Auto transformer. That's why it is wrong. It is wrong because auto transformer will give variable voltage, but AC voltage, but not DC voltage. Okay, generally we think like that. Variable voltage means auto transformer. So we need a DC voltage here, not AC. For that, we need some variable voltage source. But very olden days or previous long back, we don't have any technology of variable DC voltage. There we use one generator. The scientist name who provided one of the method is Ward Leonard. This is one scientist name. So he given one method. In that method, he used one generator directly. What is the generator output? Voltage. That voltage he is controlling and giving to the motor. Then motor speed will change. And that method we call Ward-Leonard speed control method. Okay. Let's see what is that method. First, write one point in your book. Right. In practical, the motors are designed with fixed insulation. The motors are designed. The motors are designed for fixed insulation. Fixed insulation. The motors are designed for fixed insulation. Hence, it is not preferred to increase the voltage. It is not preferred to increase the voltage above rated. Above rated. That's why we should never increase the voltages above rated. Only below rated you can do. Okay, same point for induction motor also. Right, studying now. Ward-Leonard speed control method. Ward-Leonard speed control method. Ward-Leonard speed control method. So in this method, he taken two machines. One is operating as generator and other is operating as motor, and both are coupled, electrically coupled but not mechanical. Means generator output we are giving to motor as the input power. So take the figures for this. Take the figures. Plus minus bus bar DC mains. So this is a generator. Second one is motor. So this is the separately excited motor. Field winding, separate voltage source, and armature is having voltage source of V from generator output it is. Now generator means again it requires a mechanical input, prime mover input required. So it is mechanically coupled. That this is a prime mover. This is prime mover or turbine it is. So prime mover means you can use it is as like another motor, some DC shunt motor, armature resistance control to reduce the speed. Like that, you can use some other motor it is. Now this is our generator. EMF induced in generator is EG and terminal voltage is V. And this voltage is given to motor as input. Now a current will flow in armature of motor IA. This is motor field winding, field current of motor. And here it is provided to interchange the switches also. So what is the purpose we see later. First directly connected. First complete the figure all of you. Two machines, separately excited generator, separately excited motor. Alternate source means solar power, wind power. So we need to increase solar power generation mainly, that is. Okay. So solar power, thermal, hydral, these are all after some years, it is difficult to maintain. That's why we have to increase solar power generation. Yes, voltage rating insulation will be there for house wiring also, because in house wiring, we don't use the same thickness of copper wires. We use different thickness. For fans, lights and all, we use 1 square cable. And if you take motors, like hydraulic motors or refrigerators and all, we use 2.5 square meters. And if you take ACs, air conditioners, geysers, for all these we use 4 square this thickness of meters. Cable wires, these wires, copper wires we use. They also have different insulation, not there. Whatever the insulation is there over that is also will change thickness of insulation. That's why cost of these wires increases. Okay, everywhere we have insulation voltage dependent. Yes, voltage proportional to speed only. Theoretical or practical, both are same. No, till now we don't have sound energy to electrical energy conversion. Okay, so you try to invent, then definitely you will get popular in the world. Completed figure. Three AC machines. Which three AC machines? See, if you ask about machines, I will say the four parts are easiest only. Nothing is difficult. Everything is like this only. Is any difficult here? Four parts are easy only. So don't neglect any topic: transformer, induction, DC, synchronous. First, try to complete the four parts. That means 10 marks in your hand. 10 marks in your hand. Maybe it is 12 or 13 marks sometimes. Okay, let us neglect that also 2, 3 marks. But 10 marks surely in your hand. Okay. Not cascade connection of induction motor, because cascade we coupled mechanically there. Mechanical coupling will be there. But here there is no electrical coupling. There the rotor of two induction motors we mechanically coupled, and the rotor slip ring output we given to the other motor, auxiliary motor, as input supply there. Okay, but here only electrical coupling. So tomorrow we complete DC machines. So the easiest subject in total electrical is machines, only the easiest. Maybe for first time when you listen anything new, at that time maybe it is difficult, but second time you try to revise revision, definitely it is easy one. Okay. See, particularly for machines, so most of the people at the last moment somebody will leave this. Why? Because it is little lengthy one. For revision, it will take so much time. So my suggestion for all of you, don't keep these particularly machines up to before 1 month. So you have to complete at least one revision or mostly two revision if possible before December or up to December. Up to December, you should complete revision also minimum 2 times, because before 1 month of examination, it is very tough to revise machines, because as it is lengthy subject, don't keep it up to there. Okay. So the IIT score must be, or you should have the rank of minimum 2 to 300. So recently for 500, 600 also one student got IIT. But that depends. That depends. Every year we cannot say same rank will get IIT. See, don't depend on only volume 2 problems. So you whatever you are able to solve, solve in that. If you are not getting, leave that. Don't keep on staying on the same question. Okay, there may be some printing errors or values errors will be there. So whenever it is not coming, just leave the question, go to the next question. If whatever is completed, you complete in volume 2 everywhere, wherever it is, any questions, previous gate or previous ESC, anywhere, whatever you are able to do that. Okay, so my guarantee I will you will do 90% of the questions there directly. If some 5 to 10% questions if not coming, leave that and proceed for next questions. Like in standard books, we have some example questions. E.S. Bimra and Nagratan Kothari and also J.B. Gupta. So these three maximum enough. No need to go any other textbooks. Don't waste your time unnecessarily reading many books. Not at all required. These are all wasting your time. Just follow complete notes 2 to 3 times as a revision. After that, go to standard books example questions and previous gate and ESE question. If anywhere you stuck, just leave that type of question, because that type of questions are rarely will get. Whatever is something difficulty is there, leave that questions. Okay. So rank minimum is for what minimum? PSUs. PSUs will get mostly up to 600-700, sometimes up to 1,000 also. That depends on interviews. And if there is a more number of PSUs offered, then up to 1,000 we can expect. Cutoff marks means I don't know exactly. You have to refer in the website. It is volume 2, whatever possible, able to try to solve. Power electronics, easily you can remember in each and every topic of power electronics. Take a short notes. That is only the best. Each and every topic: rectifier, half wave, full wave, control, uncontrolled. So different types we have. So for everything in one page, write the heading and write the formulas for average voltage, RMS voltage equation, power factor, all write in one page. Like that, total all topics. Okay, let's continue. See this, we need to control the voltage of motor. We need to control the voltage applied to the motor. There are two cases. I will take it as two cases. That is case 1. In Ward Leonard speed control, he only not provided about voltage control. He also given flux control. Ward Leonard speed control means not only voltage control. In addition to voltage control, flux control also there in this. Okay. See first, two cases are there. Case 1. Case 1. First I will take voltage control method. First I will take voltage control in this. So when we do voltage control, you need to keep flux is constant in the motor. You should not change any flux in motor. That is, let us keep the field current of motor constant. When it is constant, flux in motor also constant, never changes. Okay. Now, initially consider the voltage applied is rated voltage. Now motor is running at rated speed. Motor is running at rated speed. Now we need to reduce the voltage. To reduce the voltage, first you need to reduce the EMF induced in generator. How can we reduce the EMF induced in generator? So we have the equation Eg proportional to speed and flux in generator. Tell me, in order to reduce the EMF of generator, which one you preferred? Reducing the speed of prime mover or reducing flux in generator? Which one do you prefer? Tell me. Speed, flux. Okay. So if you given speed and flux, most of you giving speed, but easiest one is flux. Why? Because see, I will tell you one logic here. If you reduce the flux in generator, EMF reduce. To reduce the flux in generator, what we have to do? Field current of generator we have to reduce. When field current reduce, flux in generator also reduces. How to reduce the field current? Increase this rheostat value here. RE increases. some resistance added in this. Then field current reduce, flux reduce, EMF reduce. Whenever EMF reduce, the voltage across motor also reduce. Whenever voltage reduce, what is the speed of motor now? Also reduce. But some people are saying reducing the prime mover speed. Reducing prime mover speed. Is it easy? Is it easy to reduce? Speed reduction is simple or flux reduction is simple? Adding a resistor, that is simple, no? Speed reducing means it is a prime mover. Prime mover means like a motor operating with resistance control. So you can reduce. Now what is my logic here is, when you are reducing this speed now, then without generator and all, you directly mechanically couple this prime mover to motor shaft. Now prime mover speed reduce means motor speed also reduce. Then is this much process required again? Not required. If you are able to reduce the prime mover speed, directly mechanically couple that prime mover to motor itself. No need of generator again. Directly motor speed reduce. So this is not preferable. Here, why it is not used? The best and simple method is adding resistor in generator. Generator voltage decreases. That is given to motor. Motor speed also reduces. So in the voltage control, adding a resistance in generator field winding, then field current of generator reduces, flux in generator reduce, therefore EMF in generator reduce. Finally, terminal voltage, that is input voltage of motor, will reduce. Therefore, whenever voltage reduces, V minus IA RA by 5. Flux in motor we are not changing, constant, only voltage reduce, speed reduce. Due to this, below rated speeds are possible in voltage control. So speed you can reduce, but reduction in the speed with voltage is very, very less. 10 RPM, 5 RPM, like that will reduce, but not so much at a time. You can observe this is in the practical labs. Okay. So this is case 1. Now what is case 2 is flux control. In the same Ward-Leonard speed control, he provided flux control also. What is that? Observe. Case 2. Case 2. Flux control. So when you do flux control, you should not change voltage of motor. Supply voltage, you should not change. Only one variation we can analyze. 2 variation means we have to go to labs. If you want 2 variation of analysis, we cannot analyze theoretically. You should go to labs. Direct practical, we can do this. See now. Let us keep this voltage constant. Let us assume initially motor is rated speed. Let initially motor running at rated speed with a flux constant previously. Now speed is inversely proportional to flux. Now if the flux reduce, we know motor speed increase. How to reduce that flux? Field current of motor we have to reduce. How to reduce field current of motor? That's why we are keeping a external resistance in this field winding of motor. Let us increase this RE value. Field current of motor reduce, flux in motor also reduce. Therefore, motor speed increases. Motor speed increase, which is getting above rated speed. Above rated speed are possible. So previously, voltage control below rated, flux control above rated. Now both below rated, above rated possible in this Ward-Leonard speed control. That's why this method we also called a wide range speed control method. This is called wide range speed control. Why wide range? Below rated you can control, above rated also you can control in the same method. That is called wide range speed control method. It is wide range. Not only this, one more he provided. What is that? Observe here. Let us assume initially Generator field normally connected, not interchanged. At that time, EMF polarity plus here, minus here. Assume that this is EG at that time. Plus we are getting, minus we are getting for motor. Now current will flow from plus to minus, current direction. Due to this, there is a torque in the motor, product of flux and IA, assuming that the torque produced clockwise direction. Torque is produced in clockwise. Okay, now motor rotating clockwise direction. You can control the speed below rated, above rated. Speed, reducing the speed, increasing the speed. Now, he also provided, let us interchange the switches here. Interchange generator field terminals like this. Observe, whenever the switches of generator are interchanged, previously normally connected, now interchanges. Whenever it is interchanges, how the field current will flow now? Plus it is. Field current is reverse or not? Yes. The field current is reverse. Whenever field current reverse, what is the flux in generator? Reverse. Whenever flux reverse, what is the EMF polarity? Also reverse. Now here you will get minus, here you will get plus. Now current IA will reverse in motor or not? Yes. Now IA in motor will reverse. Now its torque will reverse. Now in which direction motor rotates? Anti-clockwise direction. So you can interchange the direction of motor from clockwise to anti-clockwise just by interchanging generator field terminals. Okay, just by interchanging generator field terminals. Make a note here. The direction of motor, can be reversed, by interchanging generator field terminals. Now in this method, the questions important means you will get the questions like this. To increase the speed of motor, in which field winding we have to add resistance? Tell me. To increase the speed of motor in this method, we have to add a resistance in which field winding? Generator or motor? Yes, motor. When you add resistance in motor field winding, field current decreases, flux decreases, speed increase. And if you want to reduce the speed of motor below rated, to reduce the speed of motor, in which field winding we have to add resistance? In order to reduce the speed of motor, in which field winding we have to add resistance? Generator or field? Generator or motor? Generator. Yes. Why? Because if you add resistor in generator, field current decrease, flux decrease, generator EMF decrease, then its voltage decrease, that is given to motor speed decrease. Okay, so this type of questions. Now you should get one doubt if you are properly analyzing this topic. Any doubt are you getting? Regarding this point, are you getting any doubt? No doubt? Not circulating. Yes, generator rotor you can reverse, but simple one other thing is observe. How to reverse the direction of motor? How I said? By interchanging generator field terminals. EG will reverse, V also reverse, IA reverse. As IA reverse, torque will reverse. This is one thing, minus IA, torque will reverse. Now I can reverse the direction of motor by interchanging motor field terminals or not? Yes. If you interchange motor field also, torque is what? Minus 5. motor flux will reverse into Ia. Now also torque will reverse. Then why it is not answered? Tell me. We can reverse the direction of motor by interchanging motor field terminals also. But why we are saying only generator? Okay, so this type of doubts definitely we get. But answer is the direction of motor we can interchange by generator field terminals only. So if you are thinking like this, and you can say that motor field also correct, but your answer they will give wrong. Why? Because what Leonard did not provide that one. Whatever he provide, we have to follow, no? Otherwise, in what Leonard speed control method, how to reverse the direction of motor if they ask, we know that if motor field terminals, if it interchanges also, motor direction will reverse. But if you think like that and if you give that option, that will be wrong, because what Leonard did not provide that interchanging of motor field terminals. He provided only generator field terminals. That's why that is only the answer. Okay. Flux control simple only na here. How to change the flux in motor? Keep the voltage constant. Add resistance in motor field winding. Whenever resistance added in the motor field winding, field current reduces. Whenever field current reduce, flux in motor also reduce. When flux reduce, the speed of the motor increases because inversely proportional to flux, no, it is same. See, we have different methods to change the direction of motor. See, that's why that is the problem. I should not raise any doubt. If I raise the doubts, no, definitely you will get more doubts on that. Okay. So just I am saying like this also we can change, but he did not provided all that provisions. He did not given according to his method. That is what Leonard method. So if you are thinking in different ways to change, then put your name and say that is your control. Okay. Okay. So like this, in this method, we can control the speed below rated, above rated. So many advantages are there. But what is the main disadvantage of this method? Tell me. The main disadvantage. Only for voltage control purpose, he taken a generator. Is it economical? Is it economical? Only for voltage control, here he is using two machines. Generator, motor anyhow required, and generator also he taken. This is not at all economical. We can buy a motor. When to operate that motor, can you buy another generator? Like buy one get one offer? No, because costly that is not 100 or 1,000 rupees motors generators. That's why it is not economical. That is the main disadvantage of what Leonard speed control. What is the disadvantage? As this method requires, as this method requires a generator setup. Generator means again prime mover for that. That is also cost. Generator setup to control the voltage. Mainly for voltage purpose, it is used to control the voltage. Okay, which increase the size and cost. The size and cost. Okay, so nowadays, how can we change the voltage? Just by using rectifiers or choppers, anything. Using these power electronic converters, rectifiers. So simply use a static rectifier, small device, low cost, less maintenance, less size compared to generator. So AC to DC converter. And this DC we will give to motor, variable voltage by changing firing angle. That is simplest one and cheapest one. So nowadays we never use this method, but still we are learning about this because we should know what is previously disadvantages, now what is advantage. Okay, so this is voltage control. Now we use same voltage control for series motor, that we will see now. Just wait for 2 minutes. We can use for series. Why we are considering this is, if you go to traction, because what is the application of series motor? Mainly in traction we can use. So in a traction we don't have single series motors, single. So based on the capacity required, suppose take a train, right? Based on the capacity of load in a traction, in the engine we don't have single motor. Maybe we have two motors mechanically coupled, three motors mechanically coupled, or four motors mechanically coupled. So that depends on the capacity of that engine. If you see sometimes in the goods trains, particularly goods, the weight is very high because goods trains, very lengthy trains, very and more number of coaches we use in that for goods. So their single engine is not sufficient sometimes to drag that. At that time we couple two engines. Suppose each engine having two motors inside. Two engines means total four motors it is. When you because of that connection of two engines and four motors in cascaded, then your starting torque and running speed will increases. Okay, based on the capacity we use number of motors in a traction, not single series motor. Single series motor may not give the complete requirement. That's why we use two motors, three motors, like that. So any number of motors, series motors used in traction. Now in the same traction I'm considering two identical motors, two identical series motors I am considering in a traction. Now that motors connected in series, also connected in parallel electrically. Mechanically they are always coupled inside. Mechanical coupling will be there, but electrically we can change the connections. Series, parallel we connect. Let us consider first series connection. Series connection. Considering the two motors series connected like this. Series connected. Assuming constant power case, it is same voltage, same current we take. Supply voltage V, current is IA. This is series connection. Whenever series connected two identical resistors or two identical any machines, what is the voltage across each machine now? Total voltage V. Series means equally divides. V by 2 here, V by 2 here. Voltage equally divides. What is the current in both now? Same current. Series, na, it is. Same current will flow in both motors. So here we will consider mainly two parameters, speed and torque, because at the time of starting, what is important? Torque important. To drag the heavy bodies, torque should be very high. So torque is important at starting. But once it comes to running condition, what is important? Running condition. Speed, high speed is important. We need to rotate that loads at high speed. For that, speed is proportional to EB by 5. Now, approximately EB means V minus IA RA, like that. So that IA RA drop and all neglecting. V by 5 it is. Speed proportional to voltage across motor divided by flux. Similarly, torque is proportional to product of flux and armature current. Okay. Remember these two relations we apply for all connections. First, series. Speed in series proportional to voltage across motor. What is the voltage across each motor? V by 2 divided by flux. Flux proportional to current. What current? IA here. That's why IA. This is V by 2IA. Speed in series. Similarly, torque in series proportional to flux and current. Flux proportional to same current IA. So IA square, IA into IA. IA square. This is the torque in series connection. Series motor, series connected. Next, same series motors. Let us take parallel connection. Next one is same series motors. I'm taking parallel connection. Parallel connection. Parallel. Let us consider the two series motors parallelly connected. Both are parallelly connected. So I said constant power. That's why same voltage, same current I am taking VIA like previous. Whenever they are parallelly connected, what is voltage across parallel combination? Same, V only. But current IA divides two halves. IA by 2, because identical motors we taken, half of current divides. Okay. Now if you apply, they are mechanically coupled inside. They are mechanically coupled. Whether it is series or parallel, mechanical coupling will be fixed. It won't change. Electrically we can change it is. Observe now. Speed in parallel proportional to, according to these relations I'm writing, voltage across motor by flux. What is voltage across each motor? V divided by flux in each motor proportional to current. What is the current now? IA by 2. IA by 2. Therefore, speed in parallel proportional to 2V by IA. Similarly, torque in parallel proportional to, according to relation, flux IA. Flux proportional to same current. What is the current here? IA by 2 into IA by 2. Current is IA by 2, not IA. IA square by 4. Okay, IA square by 4. Now, therefore, let us compare series and parallel connection from these relations and these relations, comparing both the speed in parallel to the speed in series equals to, what is the speed in parallel? 2V by IA. Previously, V by 2IA. 2V by IA divided by V by 2IA. Now VIA cancel, it will be 4. Therefore, the speed in parallel connection is 4 times that of series connection. Okay. Similarly, torque in series to the torque in parallel. What is that? Torque in series is proportional to IA square. Torque in parallel, IA square by 4. IA square divided by IA square by 4. IA square cancel, it is 4. So torque in series is 4 times that of torque in parallel. Now, what is your observation? Generally, at the starting condition, we required high starting torque. Which connection is giving high starting torque? Series. The torque in series connection is 4 times that of parallel connection. Whatever you get in parallel, that is compared to parallel, series connection will give very, very high starting torque. And parallel connection will give very high speed. It is 4 times that of series connection. That's why series connection we preferred for high starting torque. Series connection is preferred for high starting torque at the time of starting. It is preferred for starting purpose. Simply, it is preferred for starting condition. And under running condition, we use parallel connection. Now you should get it out. Okay, I won't tell, I don't rise. So these connections are pre-arranged connections, because at that time we don't open series connection and we don't join in parallel motors, because that much time we don't have motor. Train started and moving condition. At that time we don't open the wires and we don't connect. It is switch operations only. With switch, switch is closed one side, let series connection, it is operating. Once you throw the switch to back side, it will operate as a parallel connection immediately. These are all pre-arranged connections. Okay. So like that, if you take 3 motors in series, suppose 3 motors in a traction, then if you connect in series, how much starting torque you get? 9 times of parallel, and speed also 9 times of series. If motors increases, capacity increase, strength increase, speed also increases, torque also increases. But main thing required for high capacity load is torque. The main thing required is torque, because whenever load is very, very high, to pick up that load or to drag the load, torque should be very high first. Speed is not important there. Goods trains will never move at high speed. Low speed only they go. But important is torque. To drag it at the starting, because inertia is very, very high at stationary condition. To drag that, so much torque is required. Okay. Series to parallel connection will be there. Switch connection will be there. Immediately we can change. Clear? But in this method now, it is a voltage control or not? This is voltage control only. How voltage control? See, at the time of starting, how much voltage we applied for each motor? Half of the rated voltage applied. Half applied. Voltage small, less, means speed is less here. Once you converted to parallel, how much voltage applied for each motor? We only applied. Means voltage increase. Increase means don't say that it is a high. How can we increase voltage? Previously, half of the rated only applied. Now rated applied. Okay, that is not more than rated. Rated only applied. So as voltage low to high, now little speed also increases. So voltage control indirectly it is. Yes, flux also there. That's why it is purely not suitable. But anyhow, we are getting speed variation here. Okay. Here flux control also there. That's why it is purely not voltage control. No. Only voltage control for separately excited motor. No other motor. So let's see some questions. Then we go to braking of motors. What is answer for this? Okay, so all are right, but examiner is wrong here. So we are all right, but examiner is wrong. Because what is wrong? Yes, very good. Shunt is wrong. Ward Leonard speed control we are using for separately excited motor, but not for shunt motor. So maybe the examiner see how they will give questions. They want to create something new so that we are confusing. But anyhow, only one thing we know, that the speed control of motor in both directions, positive, negative, we know we are discussing only in Ward-Leonard speed control. That's right. That is only the answer. Next question. What is answer for this? So for this question, you no need to take so much time. Just in one, not 1 minute, 30 seconds, give the answer. Yes, very good. The answer for this question is, this is previous ESC question also, not only get previous ESC question also. See, this question you can answer from drive concept. What is that? Power speed variation. This is rated speed, above rated, below rated. Below rated, what is the power? Variable. Above rated, what is the power? Constant. Now, what is the question? Read once. A 50 kilowatt DC shunt motor is loaded to draw rated armature current at any given speed. Okay. When driven, first point here, when driven means when rotating at half the rated speed by voltage control. Actually, for shunt motor, voltage control not at all suitable. Then how it is? Because they given, we have to follow. Okay. Okay. Anyhow, don't confuse, because I am raising so many doubts to you. You should not get any doubt. Just read the question and answer. A 50 kilowatt DC shunt motor is loaded to draw rated armature current at any given speed. When driven at half rated speed, half means this is rated, half means here, half rated speed by voltage control, and second at 1.5 times rated speed by flux control. 1.5 means this is rated, 1.5 means somewhere 1.5, this is half rated. Okay, field control, the respective output powers delivered by the motor approximately dash. Whatever this 50 kilowatts is there, that is the rated output of motor. It is the rated output. Initially, where it is driven, half. Half means at the half exactly, power linearly varies. If it is 50 rated or full load, then what is this power? 25. So at half rated speed, it is delivering 25 kilowatts. Now at 1.5 times rated speed, it is delivering 50 kilowatts. So 25 and 50 is the answer. Okay. Next question. Try to answer this. Read the questions with patience. Question may be look lengthy, but nothing will be there in the questions. Try to read with some patience. See, that is not possible below rated. The given question, that's why I'm saying you whatever is given question, you follow the question. That's it. No one can do anything because the examiner given like that. What we can do? Shunt motor below rated with voltage reduced, volt speed almost same. It won't reduce, but the given statement like that. Follow that statement. With an armature voltage of 100 volts and plated field winding, the speed of a separately excited motor. Field is rated, means field current constant flux. Now armature voltage is how much? 100 volts. Armature voltage means supply voltage V. This is 100 volts given. Okay. Armature current is IA 10 amperes. Armature resistance 1 ohm. At that time it is running at a speed, see, 1000 rpm. N1 equal to 1000. Okay. The load torque of the fan varies proportional to square of the speed. Okay. Anyhow, neglecting rotational loss, the value of voltage which will reduce the speed of motor to 500 rpm. That is the question. Voltage control it is. What is the speed required now? 500. How much voltage we need to apply? That is IA unknown for us, because torque condition is given. IA we have to calculate. RA we have 1 ohm, and back EMF also unknown for us. So you need V. V equals to EB plus this IA RA. Try this. How much voltage we should apply so that the speed reduces to 500 rpm? Yes, very good. The answer is 47.5 volts. 47.5 is correct. Simple one. Simple one it is. First EB you can find. How? EB proportional to N5. What is the flux in motor? Constant proportional to N. Previously, you can apply directly EB2 by EB1 equals to N2 by N1. What is EB2 now? This is EB2. EB2 is N2 500, N1 1000, EB1. What is EB1? Calculate here. EB1 equals to 100 minus 10 into 1, 90 volts. So this is 90, means 1 by 2, 45 volts it is. EB2 45. Now IA we have to find. Use this condition. In a separately excited motor, electromagnetic torque proportional to product of flux and current. But what is the flux in separately excited? Constant proportional to IA. So IA proportional to both equated. IA proportional to N square. Use this relation. IA2 by IA1. IA1 equals to N2 square by N1 square. What is IA2? 2.5 amps will come. Check it is. Now substitute here. 45 plus 2.5 into RA is 1. 47.5 volts. Easy question. Okay. All of you got it? Completed? Answer this one. A 200-volt series motor, when operating from rated voltage, driving a certain load, draws 10 amps at 1000 rpm. First, draw the figure. Don't read the question 100 times also. Whenever you read one time also, draw the figure first. 200-volt supply. Current is 10 amperes. 1000 rpm speed. And its resistance totally 1 ohm. Calculate EB1 first. EB1. 200 minus IA 10 into total resistance given as 1 ohm. This is 190 volts. Now what is question? At same supply voltage, the load torque increased by 44%. Okay, the speed of the motor is dash. Load torque increased by 44% means internal torque also should increase or not? Yes, that means both proportional. They given here load torque value. So previously we have seen some questions load torque proportional to square of the speed like that. Now they given some percentage directly here. Load torque increased by 44% means electromagnetic torque also should increase by same 44%. Or both equate both. What is load torque? Load torque 44% means T2 by T1 we can take electromagnetic torque also should increase by 44. Previously there is some torque. Assume rated torque. Now torque increased by 44%. T2 by T1 equal to IA2 square by IA1 square. Why? Torque proportional to IA square. Series motor it is. Torque proportional to IA square. T2 means how much? 44% torque increase. If previously T1 is 1, now 1.44. This is equals to IA2 square unknown for us. This is IA1 square. What is IA1? 10 square. Calculate what is IA2. Calculate what is IA2. IA2 how much? We need to find the speed here. EB2 you will get once you know IA2. EB2 equals to 200 minus what is IA2? 12, right? IA2 is 12 amps. 12 into total resistance is 1. This is 188 volts. Therefore, N2 by N1. Use that. N2 by N1 equals to EB2 by EB1 into 5 1 by 5. Now N2 equals to N1 is given already. How much? 1000 into EB2 is 188. EB1 is 190 into 5 1 by 5 2. Flux proportional to current 5 1 5 2. 5 1 means IA1 10. 5 2 means 12. 10 by 12. What is the answer? Speed. New speed how much? 824. Yes, right. If they don't give flux proportional to IA also, that is our responsibility. Series motor flux proportional to IA, torque proportional to IA square. These are all our responsibility. If they don't give also, we have to take it. The speed is 824 or 825 around RPM. Okay. Magnetic circuit linear means saturation is not there. Generally, if current increase, no. If current continuously increase, our main flux also increase. Flux proportional to IA. So the given magnetic circuit is assumed linear, means no saturation, because once it's saturated, torque will be only IA, not IA square. Then you should not take IA square here. Suppose if they say that under this region saturation is there. If there is a saturation, torque proportional to only IA after saturation. So they said non linear. Linear means no saturation. That's why IA square only will come. Okay. Flux proportional to IA, magnitude of current changing, no? That's why we cannot cancel that. Last question in this voltage control. See the question. Answer this. A DC series motor driving an electric train faces a constant power load. It is running at rated speed. Initially rated speed. No values here per unit related question. Rated speed means 1 per unit. At rated voltage means 1 per unit. If the speed has to be brought down or reduces to 0.25 per unit, the supply voltage has to be approximately brought down to dash. How much voltage we should apply? See, nothing is there in the question. Per unit related. This type of questions important in competitive examinations. Calculators not required. Easily you can solve these questions. See the condition given in the question power. So if we take constant power P1 equal to P2, input side, V1 IA1 equals to V2 IA2. But in the question, they did not given about IA1 IA2. If you know IA1, see V1 is there, 1, V2 is there, V2 we need to calculate. IA1, IA2 unknown. So directly we don't get. So use the same power condition with respect to output also. What is the output power? Input power constant is output power also constant. What is the output power equation? 2 pi nt by 60. 2 pi by 60 gets cancelled. N1 T1 equals to N2 T2. N1 as it is series motor proportional to IA1 square. N2 IA2 square. Now from this N1 is what? 1. IA1 unknown. N2 is 0.25. IA2 also unknown for us. Now from this you will get one relation. IA1 is root 0.25 is 0.5 IA2. So one current relation you get. Substitute this relation in the above equation. Therefore, V1 is 1, IA1 is 0.5 IA2. V2 we need to calculate IA2. IA2 cancel. Then V2 is 0.5 per unit. So we need to reduce the voltage to 0.5 per unit. Option B correct. Okay, easy questions in per units. Now brake. Brake means not our brake. Braking of motors. Tell what is the need of brake. So don't write in your notes BREAK. Meaning will change. Right? BRAKE. That is only brake required. What is the need of brake? To rest. That is for us. Machines, for machines, we never give brakes. When we give brake to machine, when we apply brake in machine, whenever we want to brake or whenever we need to protect something, we will give rest or brake is applied on the motors. So what is the main purpose of that braking of motors is in order to stop frequently. In order to stop motors frequently. Why we need to stop the motors? Why we need to stop the motors? To protect. To whom we have to protect? To whom we have to protect? Loads. Because motors are driving some loads in industries, commercial purpose. If you see industry, manufacturing side or anywhere, motors are driving some loads. Paper mills, let us take. Motors is driving everything, printing, everything is due to motors only. Suppose in the rollers, some object is dropped. For example, we need to stop the motor immediately because that object may damage if it is rotating for long time in that, it will damage. So we need to stop the motor. Then we apply brake. So to stop the motor means if you remove the supply, it comes to stop, but not immediate, So whenever we remove supply to any motor, the motors will not stop immediately. It will continue to rotate for some time due to kinetic energy stored in that. So to stop the motor within some 2 seconds, 3 seconds or 4 seconds, within 3, 4 seconds, we need to apply some brake in the motors. Okay. What are the brakes we have? How many types of brakes we have? How many types of brakes we have? Three types. So I'm not asking electrical brakes. I'm asking how many types of brakes we have. Mainly two types. Mainly two types. Mechanical brake, electrical brake. Mainly two types of brakings we have. We call mechanical braking system. Mechanical braking system. And second, electrical braking system. Electrical braking system. Two types of braking. This is we represent simply MBS. We call EBS. Like in mechanical braking, we have so many types again, like air brakes or disc brakes or drum brakes, like the different types of braking system in mechanical. Different types, hand brake, leg brake, with brake shoes we apply. In motorcycles, we use brake shoes. So when you apply leg brake on that, the brake shoes will go and attach the brake drum tightly so that the friction produce and which reduce the speed of the vehicle. That is brake shoes we use there. Like that, we have so many disc brakes also. Disc brake, air brakes, like that different types of braking system in mechanical braking again. In electrical braking, we have three types mainly. What are that? What are the three types? One is dynamic braking, also called resistance braking. Second, plugging or reverse current braking. Reverse current braking. And third one is regenerative braking. Regenerative braking. Three types we have. Regenerative braking. Now, which brake is efficient? Mechanical brake or electrical brake? Tell me. Which brake is the efficient brake? Mechanical or electrical? Okay. As you are electrical, you are saying electrical brake. And if mechanical student, if you ask mechanical brakes, then who is best? So my answer is no brake is efficient. No single braking is efficient individual. Why? Suppose I given a task to you. I given electrical brake, I given mechanical brake. So there is a train, there is some rotating body, suppose. I said you stop that. At any condition, you stop that. Can you stop you with mechanical brake? 100% guarantee can you give? Or with electrical brake, can you stop that rotating body? 100%. No guarantee in this, because there is failures of mechanical brake, there is failures of electrical brake. Electrical brake is very dangerous. Dangerous in the sense it may fail many times, because electrically, if any wire gets open, brake fail. Mechanically also it fails. Many times it fails due to hydraulic system problem, or brake shoe problem, or brake wire problem. There are so many reasons again. Brakes also fails, mechanical brakes. That's why single braking is never efficient brake. Efficient or best braking in the sense, which one is the best braking? The combined braking system is the best braking system. What is example for combined braking system? What is example for combined braking system? Where we use that? Okay, I'm not. So, okay, cars and all, most of the people don't know, but whatever is known, that is what? Trains. Simple one. Train. What is the brake we are using in trains? Both electrical plus mechanical. Have you observed electrical brake when they apply mechanical brake? We can observe this. Electrical brakes is applied at high speed operations, because there are some advantages and disadvantages of this braking. Mechanical brakings are not suitable at high speed application. If you apply high speed at high speed, if you apply mechanical brakes, you know what happens in practical. Suppose in motorcycles, at high speed you applied brake, so you are not at that place, you will be at some other place after some 10 feet 20 feet away. So that is problem. And if it is applied for motors, see, in a motor rotating at 1500 rpm, suddenly you applied mechanical brake, what happens now? Tell me. If sudden mechanical brake applied on a motor at high speed, then the complete motor will damage first. Why it will damage? At high speed, suddenly when you apply brake, what is the centrifugal force? Very, very, very high. Just like car accidents or any accidents, vehicles. Car is moving at 100 kilometers per hour. Suddenly it hits any wall or any bridge suddenly. Then what happened? Definitely the persons will come in front with high speed. No? In the same way, when you apply mechanical brake in motors at high speed, whatever the windings or coils are there inside, they will come out of the slot. Not only that, particularly DC motors, commutator brushes will damage first. Completely damages. So mechanical brakes are not suitable at high speed. So electrical brakes are best suitable at high speeds. It is suitable. Okay, that's why we use mechanical brakes for small size motors directly. Small size, no problem, but large size inertia is high. If you apply mechanical brakes, they will damage. That's why we don't use mechanical brakes at high speed. So for low speed, we prefer mechanical brakes. For high speed, we prefer electrical brake. Suppose if anybody asks you which braking is the clean braking system, which braking is clean braking, mechanical or electrical? Which braking is the clean braking system? Yes, definitely electrical brake is the clean one. This is the clean braking system. This is clean. Mechanical braking is having not cleanness in that. That is, during this mechanical braking, some dust will release, some noise will release. Okay, noise, dust, like that. Some pollution will be there in that. Mainly dust and noise. When mechanical brakes apply, it will come outside. So this is not a clean braking system. Clean means electrical brake. When you apply electrical brake, you don't get any dust, you don't get any noise also, how brake is applied or not. But you will get one thing in that. What is that? A bad smell will come whenever electrical brake is applied. Why that bad smell? Due to heating element like resistors we use. When there is a high current, some loss will take place in this. There is some power loss that is in the form of some bad smell, like something is burning. Okay, there are some advantages and disadvantages like this. Okay, uh, let us take break for 20 minutes and come back. We see one by one. So after completion of break, if possible, we see today itself starting method. Take a break. Right, first one, dynamic or resistance braking. See, whatever the three brakings we have, dynamic, plugging, and regenerative. Out of these three, the efficient brake is which one? Efficient. Which brake is the efficient brake? Yes. The answer is regenerative braking is the efficient brake. Regenerative braking is efficient. Why? Because in this first and second braking, there is a power loss during braking. Some power will be lost. But in the regenerative braking, there is no power loss. Instead of power loss, you will get regain of power. The power is generated back. There is power saving and also generated additionally. That is regenerative braking is the most efficient braking. But out of these three, which is the fastest braking? Which brake will give the fastest braking? Means we can stop the motor quickly by which braking? The second one, plugging. Using this, we can stop the motor very quickly. Dynamic braking or resistance braking is the slowest braking. So why it is, we'll see now. Observe first one, dynamic or resistance braking. First, I will take a shunt motor. Shunt motor. Let us consider a shunt motor initially running at rated speed. Running at some speed. Running at some speed n. Back EMF is EB. This is the condition that is under running condition of motor, the figure it is. Now, if you want to stop the motor using this braking, if you want to stop the motor using this braking, so first of all, assume the motor is running clockwise direction with a torque developed in clockwise direction, because motor always rotate in the direction of torque. If torque is clockwise, motor also rotates in clockwise direction. Okay, let us consider this. Now we need to apply brake using resistance braking or dynamic braking we call. The figure for dynamic braking is like this. During this braking, we will remove completely the armature from supply and we connect a resistor in series with armature. We connect a resistor in series with armature called braking resistor it is. Supply is there as it is to field winding. ISH is there as it is. Flux is as it is. Only armature terminals. Let it is A, armature terminals. Okay. Here it is A, armature terminals. Now, once you remove the armature from supply, a current is there still. Why? Because at that instant, when you made, this is braking condition. This is the figure under braking. When you made first figure to second figure, means when connection is changed to the armature, immediately speed will change. No motor will change the speed instantly. Whatever the speed is there here, at that instant, it is same direction rotor is rotating. So there is some back EMF or not? Yes. Back EMF depends on two things, speed and flux. Speed is almost same at that time, same direction it is rotating. Flux is 100% same, constant. Then back EMF same or not? Yes. Whatever is their polarity plus minus here, with the same polarity back EMF also there here, plus minus EB. Now this is a EMF in generator or EMF in armature, just like generator. Now due to that EMF, a current will flow in the armature in the reverse direction. Observe, reverse. What is the direction of current in first figure? A to AA. But now what is the current IA? That current is due to EB only. Because of this EMF, a current is circulating in this. And that current IA will reverse. Whenever current reverse, what is the torque produced? Motor rotation clockwise only. Immediately it won't reverse or it won't stop now. At that instant, it is rotating clockwise. But the torque developed is reverse because minus here. Positive, negative, negative. Previously, torque we taken clockwise, but now the torque will be anti-clockwise direction. This torque we call braking torque. Why braking? rotation of the motor in clockwise, but internal torque is anti-clockwise. Now this torque will reduce the speed of motor. Speed will reduce. Finally becomes 0. Once speed 0, what is back EMF in that? 0, because EB and phi. EB 0. Whenever EB is 0, what is the current in that? 0. If current 0, what is braking torque? Also 0. So motor finally comes to stop. But this is the slowest braking. Slowly motor comes to 0. Why it is? The reason is, see, once braking torque is come into picture, braking torque, speed starts decreasing. When speed decrease, what is EB value? Also decrease. When EB decrease, what is the magnitude of IA? Also decrease. When IA decrease, what is again braking torque magnitude? Decrease. So braking torque is not same continuously. When speed is reducing, braking, that is opposition also reducing. Because of that, slowly motor speed reduced to 0. So this is slow braking. And what is the armature current during this? EB by RA plus RB. Now you may get doubt why there is a braking resistor here. Without that, can we directly short? If you directly short, assume that RB is 0. What is the armature current? EB by RA. This current will be very, very, very high. To limit that high armature current, we are adding a resistance. That's why it is resistance braking. Clear all of you this point? All of you clear? See, initially under running condition, torque we assumed clockwise, motor rotating clockwise at a speed n. Back EMF is this. Back EMF is always opposition, plus minus here. Once you made this second connection, how we made? At that time we open the armature and we connect to a resistor. That much time also not available for braking operation. Suppose we need to stop right now. We will apply. How? With a switch operation. We will arrange this already with only switch operation. We change from this connection to this connection within time, within no time. Okay, immediately braking applied. Then the armature current will reverse in that. Why it reverse? Previously current is coming from supply, but now current IA is due to internal EMF, that is back EMF. So as back EMF polarity will not change, remains same. As EB is remains same, IA will reverse in this. Now as IA reverse, the torque of motor will reverse. Previously clockwise, now anti-clockwise. But rotation of motor is clockwise only, rotating. But internal torque is coming opposition. That's why we call braking torque. Due to that braking torque, speed reduces. And finally 0. Okay, clear now? See, in these topics, only important is what is armature current during this break. This equation important. If you open without connecting resistor, current will flow first. If there is no current, is there any torque? If there is no opposition, is the motor speed reduced quickly? It is just like supply disconnected, whatever you are saying. Okay. During this braking, the armature is disconnected from supply. Okay, the armature current in this braking is this EB by RA plus RB. So where RB is to limit the high current. This equation important. Now what is the characteristics of shunt motor under this braking that we have to draw? Characteristics. If you remember, what is the characteristics of shunt motor first? Shunt motor, are you remember shunt motor speed torque characteristics? Shunt motor speed torque characteristics, how it is? Whenever torque increase, the speed of motor slightly decrease. So do you remember this? So our nature is to forget what is happened yesterday. Okay, no problem. So the speed slightly decrease whenever torque increases. This is motoring running operation or motoring mode we call. This is motoring operation. Now during braking operation, how it behaves? See, see, motor is running at this speed at the given torque. At the given torque or load, motor here it is rotated. At that instant, I will apply brake. Once I will apply that braking connection, at that instant, same speed is there. At that instant, same speed. But what is the torque? Immediately reverse, negative torque. That torque we call braking torque. See, when we made second connection, immediately torque reverse, but speed will not reverse. Speed is same. Now speed starts decreasing, 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 decreasing. Why speed decreasing? Because braking torque is their opposition. Due to that, speed decrease. Speed decrease, 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 and finally speed zero. So this is the braking characteristics of shunt motor, braking operation. So during braking operation, speed is positive, but torque is negative. Okay, speed becomes finally zero due to braking torque. This is the braking characteristics of a shunt motor. Okay, so this is the braking characteristics of shunt motor under dynamic braking. Now let's see for series motor how to apply this dynamic braking. Right. For series motor, how to apply dynamic braking. See this. Let's consider a series motor running under normally rated speed. Series motor is under normal running condition IA at rated speed N. Back EMF EB. This is under running condition. Now, if you want to stop the series motor by applying resistance brake, what is the condition? Same as previous. However, we use shunt motor, same as it is. What is that? Under running condition, it is running at suppose rated speed, then we apply this braking. So during that braking, the armature is disconnected from supply completely. The armature is disconnected from supply and connected to a resistor. Same procedure apply for series motor also. So try to draw in your diagrams how you will draw. Try to draw this in your figure. Disconnect the armature from supply and connect to a resistor. Try this, the figure of this. You should get idea how to make it is a resistance break. So when braking is required for series motor, the figure will be like this. So here you no need to take supply again. Remove the supply completely from this motor. See, like this we draw. Like this. No need of any supply for series motor during brake. No need of any supply. Like previous shunt motor, we given supply to field winding, but here you no need to take. And this is the connection for series motor. Observe here. Once you remove the supply and connect it to a resistor through series field winding, that is important. And how to connect is the field current should not reverse. See here. Now internally there is back EMF here plus minus. Same polarity back EMF is there. Same polarity back EMF is there because direction of rotation is same. It won't change immediately. Same direction it is rotating at N. At that time current IA will reverse because now there is no supply voltage. Previously supply voltage is there, that's why current is going like this, but now current is in this direction. Okay, flux proportional to IA, same direction of flux is there, no change in flux, only current IA reverse. The current is flowing through this braking resistor. Now due to that internal EMF, some current will circulate through this. Then what is the torque proportional to product of flux and current IA reverse minus IA. So due to that torque will reverse, that is we call braking torque. Internal torque reverse. Due to the braking torque, speed reduces to 0, same as it is previous shunt motor. Okay, got it all of you? Let's see the braking characteristics of, you don't get negative speed here. When speed 0, what is EB? 0. In EB 0, no current, no torque, completely 0 on. Let's see the braking characteristics of series motor. Characteristics of series motor under braking operation. Speed, torque. What is the speed torque characteristics of series motor? Rectangular hyperbola. The speed torque characteristics of series motor is rectangular hyperbola. Okay. Now let us assume motor is running at some speed here. Here motor is rotating. Here motor is rotating. Then I want to apply brake on this. Here motor is rotating. At that instant, I want to rotate the motor. I want to brake. I want to stop the motor. Now let us make the second figure immediately. So if you want to apply brake, change the connection to this one. Then immediately torque reverse, that is negative torque. The torque is now negative. That torque we call braking torque. Due to that braking torque, again speed of motor starts reducing. How it reduces? However, speed is changing with the torque in motoring operation, in same way it will reduce. Like a rectangular hyperbola shape, approximately like this it will reduce to 0. This is the speed torque characteristics under braking operation. So whatever motoring characteristics are there, take mirror image of that enough. Okay. What is the armature current in this braking? IA equals to EB by RA plus RSC plus braking resistor. Yes, only current in armature should reverse. That is, we are arranging the motor like that. Current in armature only reverse, but not field winding. Otherwise, flux also reverse, then torque will not reverse. Only one should reverse, either current or flux. Next, second method is plugging. Second method is plugging. This is also called reverse current braking. Reverse current braking. See, shunt motor. Let a shunt motor initially under normal running condition. Under normal running condition. At some speed n, it is rotating. This is under normal running condition. Okay. Now we want to apply brake using plugging method. Plugging. So what we do during plugging is we don't disconnect the armature now. Previously we disconnected. Now we don't disconnect. We connect the armature to the supply still, but we connect in reverse. We will connect it in reverse like this. Armature is reverse connected. Armature is reverse connected with respect to supply terminals. So these are all pre-arranged. Don't ask how it is connected at that time, these many connections. These are all pre-arranged only with switch operation. Switch operation, we do all this. Plus minus. Now armature current will flow in the reverse direction through the armature. See, here in first case, it is running in clockwise direction with a torque in clockwise direction, assume. And back EMF polarity is opposition to supply voltage always, EB, plus here, minus here. Now what is the armature current in normal running condition? Tell me, IA equals to V minus EB, because opposition, EB, by RA. This is the armature current under running condition. Under running condition, this V minus EB is called voltage across armature. Generally, voltage across armature means people will confuse. Voltage across armature is V, they will say. Voltage across armature is V, physically that is, or under just starting condition. But once motor is running, some EMF is coming in armature also. That is motor or armature voltage internally. Then what is the voltage across armature means? Both combined you have to take. V minus EB is called voltage across armature under running condition. Okay. Now observe during braking what happens here. In plugging method, we don't disconnect armature from supply like previous. Now supply is coming to the armature from current is coming to the armature from supply one, IA, but in reverse direction. Observe, it is reverse or not? Current IA is reverse compared to previous figure. IA coming reverse direction due to the torque proportional to product of flux minus IA. Torque will reverse. Therefore, the torque will come inside braking operation. That is braking torque. Reverse direction. Rotor is rotating clockwise, but internal torque is opposition. That is called braking torque. Okay, braking torque. Due to that, now speed reduces to zero very quickly. Why? You can maintain high current, little high current. Still, with high current, torque, braking torque also very high. Opposition is more. So quickly the rotor speed reduced to zero. But there is a problem here. That is, once the speed reduced to zero, now it starts rotate in opposite direction. Now it starts rotating in reverse direction. So if you don't want that reverse operation of motor, what you have to do? Once the speed becomes zero, then immediately remove the supply to the motor and apply mechanical brakes so that rotor will not oscillate. Same thing will happen in the trains. I think everyone has observed this in the platforms. So whenever train, suppose train is coming to stop on the platform, then it will come slowly, and sometimes only it happens that the train little moves back slowly. Little. How it is going back? Is anybody pushing the train? No one can push the train. Then why it is going back? Because of same plugging operation. They will apply plugging up to zero speed. Once the speed zero, once the speed zero, they should remove the supply and apply mechanical brakes so that it won't go back again. But if it is not applied, there is a chance that it will rotate in reverse direction because still current is coming in same direction. As torque is opposition, after zero speed, rotor starts rotating reverse. Okay, this is the fastest braking. Now, what is the armature current in this braking? Tell me, armature current during this braking is back EMF will not change, same polarity like previous up to braking operation because same direction rotor is rotating, flux also same. That's why it is V plus EB now divided by RA. Why we are adding that resistance? Now observe voltage across armature is addition, very high voltage, high current. To reduce that high current, we are adding a resistance. This is the armature current during braking. Okay, got it? See what is again confusion. See, torque is proportional to flux IA. If current reverse, how flux will reverse? We are not talking this. This is main flux. We are not talking armature. We never talk about armature flux except armature reaction. Remaining whatever the flux we are talking completely main flux, which depends on field currents. Okay, flux will not change. Only IA will reverse. Like that, we are arranging the connections. Okay, don't confuse again in that. Clear now, all of you? Any more doubt? Right to left means how reverse rotating is tough. Just now I given no reverse rotation. If you don't want, remove the supply and apply mechanical brake. Motor will not rotate reverse again. Okay. See the braking characteristics. Braking characteristics of DC shunt motor during plugging. Speed torque of shunt motor under normal running condition first. Speed torque characteristics are drooping. Slightly torque will speed will reduce whenever torque increases. Assume that motor is running at this speed whenever we apply brake. Whenever we want to apply brake, here motor is rotating with this torque, with this electromagnetic torque. At that instant, I will apply brake. So instantly speed will not change. That's why same speed will be there whenever I apply plugging. Same speed it is rotating. But instantly braking torque will reverse. The torque in motor reverse because of reverse torque. Now speed of motor reduces. Speed reduces and becomes zero. Now it starts rotating in the reverse direction. This is the characteristics, speed torque characteristics of shunt motor in plugging case. Here speed previously the speed torque characteristics of braking mode are passing through origin, dynamic case. But for plugging case, it won't pass through origin. The speed torque characteristics are linear, and not passing through origin. That is important. Not passing through origin. Why it is not passing through origin? Torque is never zero na here. Even speed zero, torque is not zero at that time. Speed reduces to zero, still torque is there in reverse direction. Due to that, now rotor starts reverse. That's why it is the speed negative. Speed become reverse negative here. Okay, but previously in dynamic braking and speed zero, everything zero in that, because that is not from supply, but it is from supply side. That's why it is like this. Clear now? See, slopes and all, these are all not matter. Slopes, and so you take same slope. So according to figure, we have to draw now. It is same slopes or not, that we cannot define directly. Okay, any slope. So you try same as it is for series motor. See one question, previous gate question on shunt motor plugging method. See, in these two brakings, plugging method and dynamic braking, there is power loss during braking. What power loss? See here, you are adding some additional resistance in braking method. Due to that, some current will flow in the resistor, some additional power loss will take place. Same previous resistance dynamic braking also, resistor we connected. Due to that, additional power loss. Power loss will be there in the two methods. But in the third one, regenerative braking, we don't get any power loss. See one question on this. See the question. A 240-volt DC shunt motor draws 15 ampere while supplying rated load at 80 radians per second. A 240-volt DC shunt motor 240 volts DC shunt motor draws means load current, that is 15 amperes, and rotating at 80 radians per second. Omega given, speed 80 radians per second. The armature resistance 0.5, field resistance 80 ohms. If field resistance is 80, what is the field current? ISH is V by RSH. 240 by 80, how much? 3 amperes. Then armature current is, out of 15, 3 is going in this direction, remaining 12 amps in this direction. Then calculate back EMF. At that instant, find back EMF. EB equals to 240 minus 12 into 0.5. How much it is? 234. This is back EMF. EB. Now read the first question. The net voltage across armature at the time of plugging. Across armature, that is armature resistance or armature. What is the net voltage across armature? We call V plus EB. Running condition, what is the voltage across armature? V minus EB. This is V plus EB. 240 plus 234. Nothing but 474 volts. Second question. The external resistance to be added in armature to limit armature current to 125%. Means we are adding a resistor here, braking resistor externally. How much resistance we need to add? This is the current equation. But in that question, they given to limit 125%. If they don't give 125, we take directly IA. If they given 125, we take 1.25 IA equals to same equation, V plus EB by RA plus RB. Now use this equation, substitute here. 1.25 into IA is 12 equals to 474 divided by RA 0.5 plus RB. From this equation, find RB value. Breaking resistor, how much? Breaking resistor. What is the breaking resistor? Thirty-one point one, right? 31.1 ohm. So this much resistance we have to add. If it is to be limit 125% of armature current, we are adding 31.1. Okay. If they don't give this, we take directly IA. If they given 150%, 1.5, 200%, 2 IA, like that. The only thing in this breaking is you should know about current relations. That's it. Current equations for dynamic braking, for plugging. And also next we see regenerative braking. Now write one more question related to same question. One more, third question in this. Third question related to same. Write the question. In the above question, the braking torque developed is dash. The braking torque developed at the instant of plugging. At the instant of plugging is dash. At the instant of plugging is dash. What is braking torque? Torque equal to mechanical power developed by omega. Mechanical power is EB into IA, but how much current we are limiting? 125. That one you have to take here. 1.25 IA by omega. Omega directly given in the question. EB is 234. 1.25 into IA is 12. Omega is 80 radians per second. Calculate the braking torque. What is TB? Torque. Okay, see now regenerative braking, third one. So this regenerative braking, we don't have any circuit for this again, like previous plugging and resistance braking. So this braking, there are two types in this again. Which one? In that one is automatically it will take place, and second manually we will apply this. Second, manually we can apply regenerative braking and automatically it takes place. Whenever automatically it takes place, automatically it disappears. But manually when we apply, motor comes to stop. So in regenerative braking, actually, the motor never comes to stop automatically. Whenever it takes place automatically, the speed will never comes to zero. It never stops. But manually when we apply, then it is possible to get zero speed. We can stop the motor completely with manual case. Okay, let's see what it is. Now I will take an example, shunt motor. Same previous example, that is previous question data I am taking. Observe here. See, let initially motor is running clockwise direction with a torque developed in clockwise at a speed n. Now there is a back EMF in motor EV. So just previous example I am giving. What is the voltage we applied? 240 volts. Previous example, this one, 240. How much back EMF we got? 234. Voltage applied 240, back EMF we got 234 volts. Okay. Generally, under motoring or normal running condition, always back EMF EB will be less than V. Back EMF EB less than V. 234 less than 240. This is normal case, running condition. But sometimes the speed of motor suddenly increases. Assume that speed of motor suddenly increase. Why it increase? There are many reasons. Speed increase due to sudden load drops. Assume that it is belt driven motor. Belt driven, some load connected, just like your flooring mills. In the flooring mills, single motor they used to run so many mills with belt connections. Same as it is. Okay. Now there are three loads, for example. Three loads are there on that. Suddenly two loads are dropped. Suddenly two loads dropped due to belt break. Now there is only one load. Whenever sudden load reduces, the speed of motor increases. Whenever sudden load reduces, the speed of motor increases. If speed increase, what is the back EMF? EB proportional to N into 5. Flux is no change, flux constant. If speed suddenly increase, back EMF also increase. Back EMF EB also increase because EB proportional to N5. Whenever speed rises, EB increase. Now at one condition, let the EB becomes some 244 greater than 240, supply greater than the supply voltage it is. Whenever EB greater than V, what is the direction of current? Current always high potential to low potential. So as EB greater than V, current IA will reverse. Current, now armature supplying current back, supplying current to the source again. That is called regenerated power. Power is not consuming, power sending back to source. So during that condition, torque proportional to phi IA. IA become minus IA. Because of that, internally torque previously clockwise. Now internally torque will reverse. That is called braking torque. Now due to that braking, whatever the speed increases, again it will reduce. Whenever speed reduce, again back EMF reduces. If back EMF again reducing, once it comes like 239, then again it is less than supply voltage. Again current will reverse. Again normally current reverse, torque reverse. It continue to rotate as a motor again. It continue to rotate again as a motor. See, brake applied automatically disappears. So in automatic braking, you never get zero speed. Then what is the use of that braking? Yes, the most useful braking it is. How it is most useful is, take a best example is train. Let us take a train. So this is a flat track. This is a flat track. Let us consider this is a ramp track. Ramp or slope. Some slope is there. Two tracks I taken. Whenever it is moving in the flat track, then supply voltage 240, back EMF 234. But whenever the same train coming down on a track having some slope like this, that the train is coming in downward direction, in this direction now. Actually, it is the position of load like that. Position of load means having some slope here. Due to that slope, without intervention of the torque developed, the speed of the train increases. Speed of the motor increases. Without having connection with the torque, the speed will increase. Actually, with the torque developed, it has to move slowly. But because of the slope here, the speed of the motor automatically increasing. During that, internal back EMF will be greater than the supply voltage. Internal back EMF will be greater than supply voltage. During that, it will send power back to source, that is regenerator. Whenever it is sending back, current direction reverse, internal torque reverse, that is called braking torque. Due to the braking torque, it won't allow the train to move at high speed. That's why automatically speed is controllable here. Automatically speed is controllable. The train will never come with high speed. Even whatever the slope it is, the train will never come at high speed. Means it is protected or not? Yes. The regenerative braking will protect the loads automatically. Automatically brake takes place. Automatically, because of the brake speed reduce, it won't come at high speed. So derailing will not happen. Otherwise, if there is a slope and if it is moving like our motorcycles or any other, suppose what we do motorcycles, if there is a slope, to save the power, we can switch off the fuel also, and we can move at high speed also. But if the loco pilot will think like that, the train will not be on the track. Okay, that's why he no need to apply anything. Automatically the speed of train limited here. Okay. Yes. Right. Electric cars we use. Clear? This is automatic braking. Regenerative braking here automatically takes place. Now, manually. Manually, how can we apply regenerative brake? Yes, we can apply. So nowadays in trains and mostly in the local trains, in most of the metro cities and metros trains also we use this type of regenerative braking. How it is? See, generally under normal running condition, what is the back EMF? Less than supply voltage 240, EV less than V. But if you want to apply regenerative brake, suppose you want to stop the train, you want to stop the train completely, then you want to apply this braking regenerative to save the power, because power saving at present situation in India, saving is very very important because of some problems arrived in the coal and all. It is very important to save the power. So during that, suppose regenerative braking we are applying, then what happened? I will reduce the supply voltage to some 200 volts. I will reduce the voltage wantedly. If voltage reduced, back EMF cannot change instantly. Assume that separately excited motor, then only it is applicable. Separately excited motor, flux is always constant. Now voltage I reduced. Voltage reduces. Whenever voltage reduce, what happened? Suddenly voltage reduced, but back EMF will not change. Speed is same, flux is same. So at that time, EV become greater than V. Now what is the direction of current? IA reverse. Current is reverse. Regenerative takes place. So as current is reverse, internally braking torque applied. Because of the braking torque, during that speed will reduce. Little speed will reduce. Whenever speed reduce, this EV coming to reduce 230, 225, 220, 210, 200 nearly. Whenever it is nearly approaching 200, immediately I will drop this to 150. Still it is, maybe it reached 200, but still I reduce the voltage, still it is greater, still current is reversed, still braking torque is there, still speed reduced. Again, whenever it reaches nearly 150, I will drop the voltage to 100. Then again 150 greater than 100 means again braking operation, still speed reduces finally like this to 0. Like that, regenerative brake we applied manually. It is voltage reducing, supply voltage we are reducing. Due to that, internal braking torque is there. Due to that, speed of motor reduces to finally 0. Okay. Now you may get doubt why it is reduced. Why it is reduced like this 200, 150. So you can think that like directly I will reduce to 100 volts. If you reduce at instant 100, EB is 234, supply voltage 100, then what is the current IA? EB minus V by RE. EB minus V means 134. Armature resistance 0.5. This is very, very high current. Due to that high current, the armature winding may burn. So for that reason, step by step, we have to reduce the voltage. Okay, clear it is? This is manual regenerative brake. See, induction motor also same. Generally, induction motor rotates at n less than ns. Okay, this is motoring operation. But if the speed suddenly increases, no, then n greater than ns. Which operation? Induction generator operation. In a induction generator, generator means torque produced always opposition. That is itself braking torque. Because of that braking torque, speed of generate that induction motor reduces again. Whenever again speed becomes less than ns, again motoring operation will continue. Same as it is regenerative brake. So these are the braking methods. Okay, so these are the braking methods, and we have, or we see the remaining starting methods. So I will give information about 3.4 point starter tomorrow, and then yes, good. Tomorrow we see the remaining losses, efficiency calculation, and tests also briefly we see once. Okay. Tomorrow on. Tomorrow we see that. Problems on regenerative braking we don't have because it is automatically taking place. Only current important. Current is what in regenerative braking also. Current IA is during braking. Current IA is EB minus V divided by RA. That's it. Power will fed back up to EB again become less than V up to that. So tomorrow almost same 5:30 to 9 or 9:30 whatever it complete. Okay. So half an hour required for minimum starters. Then we see losses efficiency and some problems on that. And then we go to testing. See, little universal motor we see today only. Universal motor because tomorrow time may not be sufficient. See about universal motor. Universal motor. So what is universal motor statement? It is a motor which works for both DC and AC supply. For both DC and AC supply. Motor which works for both AC and DC supply we call universal motor. Now which motor is suitable like that? Series motor is suitable. Series motor is suitable as universal motor. Now series motor is suitable as universal motor. Okay. What is the difference? DC series motor, AC series motor. What is difference in these two? When we give DC supply and when we give AC supply, is there any difference in that? Yes, there is a difference. That is constructionally, everything same. In the construction, I already said, when we give DC, the stator, no need to laminate. No need to laminate stator for DC supply. But when there is AC, the stator frame or yoke we call that must be laminated and remaining everything same, no change in it. Remaining everything is same. Okay. Now let's see the figure. Let us consider a DC series motor. North pole. Series motor means how the field winding and armature winding both in series. Both will be in series. Let's south. DC series motor, north and south. Field winding, armature winding, both in series. I am not showing that here. Observe. First, we give DC supply. This is field winding connected in series with armature like this. Let DC supply given. When there is a DC supply in the armature currents, let the current flowing in armature here is cross under north pole, south under dot pole. Like this current is going inside. Now it is for this field current, I'm assuming it is acting as north, it is acting as south. Let us assume it is a north pole, it is a south pole. Actually, it is not correct. If you apply right hand thumb rule, here north will come. Okay. Here south will come. Don't consider current direction, just assume that it is a north pole, south pole. And this is the current here. Now, due to this current in this half, the current here is cross, in this half current is dot. Apply your right hand thumb rule. 4 fingers is current. In this half current going inside, in other half current coming outside. Then flux will be downward direction. That is, the armature flux is downward direction. If it is the flux, what is the pole here? South. And what is the pole here? North. This is south pole, this is north pole. Now this south is attracted towards north, this north is attracted towards south. Means this is only the torque, electromagnetic torque. Now rotor twisted in anti-clockwise direction because opposite poles attracted. So when rotor twisted, even it is twisted, all south will not come here. South is always here only. North is always here only. Now continuously there is a unidirectional torque. That's why the motor continue to rotate. This is DC series motor. Okay. Now let's consider AC supply here. Consider AC is given. AC. AC means there is positive half, negative half. When it is positive half, current will flow in one direction. If it is negative half, I will take another diagram for negative half. If it is negative half, this is for negative half. This is for positive half. When positive half is there, this is only the current, torque is anti-clockwise. Okay. Now when it is negative half, current will flow reverse direction. Whenever current reverse, let us take, so here I take an upward, here I will take downward direction. Current is reverse. Assume that current reverse. Whenever current reverse, what is the current in the armature? What is current in armature? Here previously cross dot. Now current in armature also reverse. Cross, here dot. Now check. Now apply right hand thumb rule in the armature. One half cross, fingers going inside, other half dot. Flux will be upward direction. Here the flux is upward direction. What is the pole here? South. What is the pole here? North. And previously this is not south, and now this is south, this is north. Poles also interchanges because field current also change. Poles also interchange. Now what is the current cross? Dot means here north pole. This is south pole. This north attracted towards south. This south attracted towards north. Again the torque produced is in same as previous case. That is anti-clockwise only. That is called unidirectional torque. Even if you give AC supply, there is a unidirectional torque. It continue to rotate in same direction. Now you may get doubt. So is it happen for shunt motor or not? Yes, it will happen, but unidirectional continuously will not produce. So this is clear for all first. Whenever positive and negative half it is changing, current in both field winding and armature simultaneously change. So torque produced is same direction. That's why it continue to rotate. Now let us consider, in case of series motor, what is the torque relation? Proportional to flux Ia. Flux also proportional to same current, that is Ia square. If it is positive half plus Ia whole square, if it is negative half minus Ia whole square, then it is also same Ia square only. Torque remains same. Now if you take shunt motor, now you may get doubt here. In shunt motor, torque proportional to flux Ia. When we give alternating supply to this positive and negative half, for positive half, let current is going in this direction, Ia, ISH. So due to that, a torque will produce, motor will rotate in one direction. Okay. Now when there is a negative half, current Ia reverse, ISH reverse. Then you may get doubt. Now also flux is reverse because ISH reverse minus phi and Ia reverse minus Ia. Again torque is positive. So you may get doubt again. Torque is remains same. It may continue to rotate in same direction. Yes, it may rotate, but actually it won't rotate. The reason is, when there is negative half from positive half, current Ia will reverse, but ISH will not reverse immediately at that instant. Why ISH will not reverse? Because more number of turns in the field winding. When there is more number of turns, what is the problem? The effect of inductance is very, very high. What is inductance? L equals to flux equal to mmf by reluctance, or what is the inductance formula? I think you know, mu n square. Inductance proportional to square of the turns. Inductance. If a number of turns is more, inductance effect also very high. Then that inductance will not allow sudden change in the field current. Ia will reverse. See, torque is proportional to flux Ia. For positive half cycle, it is positive. When there is negative half cycle, immediately flux will not reverse, same is there, but Ia reverse minus Ia. Then what is that? Negative means for some fraction of time, the torque is reverse, that is becoming braking. Due to that, if you give AC supply to shunt motor, it will rotate, no doubt it will rotate, but you don't get a smooth rotation of motor. You don't get smooth rotation of motor. It will like oscillating, jerking. So smooth rotation not possible, but series motor will rotate smoothly. Okay, so only series motor is suitable for both DC and AC supply, but not shunt motor. Okay. Yes, tomorrow we see questions on efficiency and also testing. Starting method also not there for gate. Testing also not there for gate. Only losses efficiency required for gate examination. If AC given, AC series motor only. That is only universal motor we treat. Okay. Okay. So I will stop for today here. Tomorrow we remain. Tomorrow same 5:30 to 9.
Sir,
Tell me, Avinash.
sir, in regenerative braking, sir, when the value of EB increases, then the torque is in the opposite direction.
Yes.
Sir, after that, please explain, sir, once what happens.
When EB increase, EB greater than V means current IA reverse.
Yes, sir.
When IA reverse
Current
started,
reverse is, yes, sir.
then braking applied because of the speed reduce.
Okay, sir. Speed reduces and again the speed will come below the.
When speed is reducing, EB again reduce. Suppose during that if EB become less than V, again motoring operation.
Okay, okay, sir. Sir, after a reduction of speed, EB again reduced then.
Suppose if speed reducing, EB reduce, EB becomes less than V means again it will continue to rotate as a motor. Same
Okay,
motor
okay, sir.
operation will continue from there. But in manual operation, we can reduce step by step up to zero speed. But automatic braking, regenerative braking, it cannot reach zero speed.
Okay, okay, sir. And sir, what is the value of braking resistor, sir?
Value of braking resistor, that maybe we cannot say 10 ohms, 20 ohms, that depends.
Okay, okay, sir.
Hello, sir. Good evening, sir.
Good evening, tell me.
Sir, before that question, braking of motor, there is one question. Could you open that, sir?
This one?
Sir, screen not sharing, sir.
Oh.
Screen is not sharing.
Okay. Tell me now.
Sir, in that he's saying that power is constant, no, sir. V1 equal V1, I1 equal to V2, I2.
Which one? Which question?
Before motor means braking of motor starting is there, no, sir. Before that question.
This one?
Yes, sir. This one only. He's saying that power is constant, no, sir. Means V1 equal to V2. From that we can say, no, sir.
But IA2 different, no?
Power constant.
Speed is changing, no? Speed. Flux will change in series motor. Okay.
Mean we should take the consideration of the flux also.
Because flux proportional to same current, no, in this. That's why.
Oh, okay, sir. Sir, one more, sir. In plugging, sir, if we want to reduce the speed, we are considering as a plugging and regenerative. Mean first one, no, sir. Sir, if we reduce the speed, means that motor will stop, means from totally stop, sir.
No. If we reduce, we're plugging, no, this.
In both methods, sir, first and second one, we are reducing the speed, means we are stopping the motor only, no, sir. Means
Reducing is not stopping, no. Reducing means speed value reduces, but not totally zero, no, at a time.
Sir, but if you consider the train example, means at the station, the motor will be stopped, no, sir.
Yes.
It means that we want to start again, means we want to start that motor again.
Oh, yes.
Means it take huge power, no, sir.
Your question is not clear to me.
Sir, actually, in the station, the train will be stopped, means the motor will stop.
Okay.
If you want to start again, means it take huge power, no, sir.
If you want to start again?
It's taking again huge power to start.
Which?
Sir, once again I will say, sir. Normally, in the plugging and dynamic resistance both methods, we are considering that reducing the speed means up to n equal to 0. Is it right, sir?
Rotating at a speed n.
Means at last n equal to 0.
Not n equal to 0. In method, speed comes to 0, braking, because of braking. Okay, then?
Sir, it means the ideally motor is stop.
I'm not clear with your question.
Sir, in first and second method, n equal to 0, no, sir. Means if you want to reduce the speed.
See, plugging, dynamic braking is different, and this one is different. In dynamic braking, we are not connecting armature to supply. Finally, the speed reduced to 0 only.
Yes,
and
sir.
and it won't rotate again back.
Yes.
But in the plugging method, what happened? As we are connecting still the armature to supply only, no? But armature is not disconnected. Still, it is connected to supply. That's why there is a chance to rotate in reverse direction in plugging method.
Yes, sir, I understand.
Hmm.
Sir, in first method means
Hmm.
we are disconnecting from the supply, no, sir.
Hmm.
Means our motor is stopped
Stop.
at last.
Hmm.
Means if you want to start the motor,
Hmm.
then we keep supply, no, sir.
We kept
Supply,
what?
sir. We
Not, it is not audible clearly. When we want to start again,
again we want to give the supply.
yes, we want to give supply. Then again reconnect back to armature supply, same as it is previous connection. Otherwise,
Means
it won't start. No,
yes, sir.
we
Means
have
in
to
new
reconnect. There is switch operation. No, suppose switch is close to front side, it is breaking, and close the same switch back to again reback. The normal operation again, motoring mode.
Okay,
Like
sir.
that, we can start.
Sir, you said an example as a plugging at the station, no, sir. Plugging plus
Mm.
mechanical braking.
Mm.
At the means which we are using the practically plugging or rigid braking in the
Both will apply automatically. That depends on, suppose take a train. In the train, sometimes automatically takes place, sometimes wantedly also we can apply manually.
Yes, yes, sir. I understand that one, sir.
Oh.
Means we are using plugging plus mechanical braking. You said, no, sir.
Yes, both we use.
Means which we are using means plugging or rigid braking. Is there any specific?
Cannot say directly because plugging also we use, and regenerative braking also we use. Mostly in metro trains nowadays we are using regenerative braking, but in the normal some of the trains we are using still plugging only.
Okay, sir.
At high speed we apply electrical brake. Once speed reduces and coming to zero nearly, then we apply mechanical brakes. Okay.
Sir, at low speed, why electrical braking is not efficient?
I don't set that point. At low speed, electrical braking also we can use, but at low speed, quickly stopped by mechanical brake. No?
Yes, sir.
That's why.
Sir, is there any more means not in the syllabus means any technological new? Is there any braking systems?
User?
Means any high efficient braking system other than three methods?
Only these three only. Electrical only three brakings available.
Mean presently we are using three only.
Three only. Then dynamic we don't use.
Means mostly rigid braking.
Either plugging or regenerative. These two only.
Okay, sir. Thank you so much.